A feedback control of a robotic arm golfing, presented by Adam Hilton, Kevin Hartman, Patrick Ogilvy, and Julianne Wilson.
We were assigned a project where we had to come up with a mechanical system and add a feedback controller to it. Being a group of mechanical engineers, we like to know how things work, and we wanted to pick something cool, like Iron Man. Okay, maybe not Iron Man, something more like an exoskeleton that an army would make. But we couldn't do all of the entire exoskeleton, so we had to pick a single limb. And to make it interesting, we wanted an arm to golf.
Our system is comprised of two components, a rigid arm made of steel and a golf club. Both of those are connected with a pivot, and the whole system is powered with a DC motor. The motor and the pivot have K and B coefficients, with the K being the spring and the B correlating to the damper. Here we have a model of our physical system. We start with the DC motor, which then creates a torque across the robotic arm, which is then connected to the golf club.
The model of this system, specifically the robotic arm and the golf club, can be shown as an impedance network. This has a torque input and the damper and spring coefficients along with the mass built in. This, simplified mathematically, becomes a theta 2 over torque transfer function as shown. This transfer function then multiplied by s gives us our output of a velocity theta 2 dot output. This is important to show the relation of the angle as a velocity.
We ran into a few initial problems when modeling the system. First off, the model is a double pendulum, which as you can see, there's a lot of free body motion between the two arms. This motion is extremely chaotic and nonlinear and therefore hard to analyze, so we had to linearize it. The two equations shown are the dynamics of the two different arms. We could not take these two equations and implement them into our system because they both assume free body motion. Therefore, we had to further simplify the equation.
In order to linearize the system, we had to simplify the dynamics. The first assumption we made, we found out later upon further study, was not valid. Therefore, we made a new assumption that took the small angle theorem into account. This makes sure that the angle between the two arms is kept small. Using this allowed us to simplify our plant model and the transfer function into a linear system.
This is the block diagram of our system. Everything we've showed you up to this point is the plant, the G of S. In the feedback loop, we also have the DC motor, as well as the PID controller, and all looped together with the feedback. To determine our values for our transfer function, we entered our variables and our function into MATLAB. Running through several iterations, we completed a trial and error and analyzed the best match according to our Nyquist, Bode, and step function plots. As you can see, we entered the standard RA, LA, and KT values, representing the coefficients of our motor. The J1, B1, and K1 values correlate to the robotic arm, and the J2, B2, and K2 values correlate to the golf club. J is the rotational inertia of the two masses, B is the damping coefficients, and K is the spring coefficients. With these values shown, we produce the Nyquist and Bode plots shown here.
This next MATLAB plot shows the new transfer function of the closed loop. The dotted line on the very bottom of the graph shows the original output. Once a PID controller with a very large integrator is added, you get the new transfer function shown by the solid line. This step function has a rise time of 0.234 seconds. This is important because with the swing of a golf club, we need to get to our desired velocity as quick as possible, or under 0.6 seconds, which is our design specification.
From the Bode plot, we can see that eta is small. This correlates to a small percent overshoot. When the calculations are done, we can find that our percent overshoot is within our specification. For our system, all our poles are stable, and the Nyquist plot does not encircle -1. From this, we can say that our system is bibostable.
In the Simulink block diagram, there consists 3 feedback loops. The first loop, marked in orange, is a feedback loop for the angular velocity of the upper arm. The second feedback loop, marked in blue, consists of a gain and a compensator. The compensator is necessary because it accounts for the zero and double pole of the theta 2 over theta 1 transfer function. The third feedback loop allows us to compare the desired angular velocity with the output velocity. It achieves the goal of the system. In order to come up with this semi-link diagram and the transfer functions that we used, we had to make a few assumptions. First, because the second arm is considered rigid to the first, but still in free motion, we decided to assume that the motion of the first arm is only affected by the motor, and not by the second arm. The second arm, however, is affected by the motor and the first arm. From here, we had to solve for theta 2 over torque, and then divide by theta 1 over torque to get the transfer function of theta 2 over theta 1. In order to make our system match specifications, a PID controller was added. Inside of the PID controller are 4 variables: a proportional, integrator, derivative, and numerical constant. The PID controls how fast the system responds, how much overshoot there is, and the oscillation of the system. The proportional controller increases the response to the system, but increases the overshoot as well. Also, it includes an error. The integrator term does a similar role as proportional, but doesn't have the steady state error. Finally, the derivative term helps with stability and settling time. Our system needed to get a rise time of less than 0.6 seconds and have an overshoot of no less than 15%. This allows the golf club to hit the ball at a range of speeds which would be deemed appropriate for a skilled golfer. Our project needed to increase its rise time, but with an oscillation around the desired output. Therefore, we decided to go with the integrated term instead of a proportional term. So in the PID controller, the P term is set to 0, and the integrator term is very high. Because the system doesn't need to settle and be constant, the need for a derivative term was negligible, so it is set to 0. In turn, this means the end constant doesn't matter. When this was run, we got a rise time of 0.234 seconds and a percent overshoot of 11.3%. Meaning we met our specifications.
However, our robot should not and could not work in real life. First, it is uneconomical. The controller would have to have a crazy high integrator, which could be expensive. Second, the dynamics behind the robot are incorrect. We made assumptions to make the system easier to handle. Third, there needs to be experimental testing before any constants can be set in stone, such as B2, K2, and J2. Finally, there is no braking system for after the club hits the golf ball, which can be extremely dangerous. In conclusion, this data should not be used in real life.